Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 1. Introduction to Two-Point Boundary Value Problems. Two-point boundary value problems are a class of ordinary differential equations that arise in various fields of science and engineering. Two-point boundary value problems involve spatial domains with a set of specified boundary conditions. In other words, such problems require the solution of an ordinary differential equation subject to boundary conditions at two distinct points, usually at the start and end of an interval. They are central to solving many real-world engineering, physical, and mathematical problems. Some common application areas include vibration analysis, beam deflection, heat conduction, fluid flow problems, chemical reaction modeling, quantum mechanics, and so on. A two-point boundary value problem is an ordinary differential equation in one dimension with two boundary conditions. Consider the following second-order ordinary differential equation, where x and y denote the physical quantities, independent and dependent variables, respectively. P, Q, R, and G are coefficients of the ODE, which may be functions of the independent variable x. While analytical solutions are possible for certain boundary value problems, in general, these problems are solved numerically due to their complexity. An ordinary differential equation alone is not sufficient to obtain a unique solution to the problem. A boundary value problem may have no solution, only one solution, or an infinite number of solutions. In the case of having many solutions, additional equations are required to be able to find its unique and complete solution. These equations, referred to as boundary conditions, arise as a result of the system requirements or constraints, which specify the behavior of the physical phenomenon at the boundary of a system. Boundary conditions represent the influence of the environment on the isolated model. In two-point boundary value problems, the independent variable is the space variable, commonly denoted by x. The number of boundary conditions required to obtain a unique solution to a two-point boundary value problem is equal to the order of the ordinary differential equation. Boundary conditions for system boundaries are constructed by specifying y and/or a linear combination with y prime. In practice, most physical phenomena occurring on surfaces can be expressed mathematically with the following generalized boundary conditions, where alpha 1, alpha 2, beta 1, beta 2, gamma 1, and gamma 2 are constants. Consider a heat-conducting rod extending along a wall, x from 0 to L. The temperature distribution Tx for this event is governed by the following second-order ordinary differential equation. The analytical solution is T equals C1x plus C2, where C1 and C2 are arbitrary constants. The temperatures at the boundaries are set to T0 is equal to 20 and TL equals 200 degrees. The true solution that depicts linear relationship is a unique solution to this case. Consider a beam with constant cross-section and length L as an example of a two-point boundary value problem. The ordinary differential equation describing the lateral deflection of the beam y is described with, where EI is flexural rigidity and M is the bending moment. The general solution without boundary conditions has an infinite number of solutions. The beam is fixed at the left end. The deflection is 0 on this end, i.e., y0 is equal to 0. The displacement on the free end of the beam is specified as YL equals minus delta, with the minus sign indicating the downward direction. There are numerous numerical methods for solving two-point boundary value problems. In this video series, the most commonly used finite difference, finite volume, and shooting methods are covered. The finite difference method is one of the oldest and most widely used numerical methods for solving ordinary differential equations. Consider the following two-point boundary value problem, where alpha 1, alpha 2, beta 1, beta 2, gamma 1, and gamma 2 are constants. P, Q, R, and G may be continuous functions of x on the closed interval from a to b, and our x over gx is less than or equal to 0. A boundary condition is referred to as Dirichlet boundary condition when the solution of a differential equation is specified at the boundary. If the solution is known at one of the boundary points, say x equals a, the BC is expressed as y equals delta 1, where delta 1 is the known solution at the boundary point, x equals a. In the earlier examples, the temperatures at the boundary points were known, i.e., the boundary condition type is Dirichlet boundary condition, T0 is equal to 20 and TL equals 200 degrees. The Dirichlet boundary conditions were applied to the beam example also, i.e., at the fixed left end, y0 is equal to 0 and, at the displaced right end, yl equals minus delta. A boundary condition is referred to as Neumann boundary condition when only y' is specified at either boundary, i.e., y'A equals lambda 1 and y'B equals lambda 2. Numerous boundary conditions in physical problems fall into this category. For instance, y'A equals 0 as a symmetry boundary condition, which implies the physical property is symmetrical with respect to x equals a, i.e., y has either a local maximum or a local minimum at x equals a. The flow of heat in the x direction is governed by Fourier's law, q double prime equals minus k dt over dx, where k is the conductivity of the medium, T is the temperature as a function of x, and q double prime is the heat flux. If the heat flux is specified, Q0 equals constant, at one end, say x equals L, then for the surface node, we have, as follows, the known or specified derivative. A boundary condition is termed a mixed or Robin boundary condition when a linear combination of y and y' is specified at a boundary node, for instance. This type of boundary condition is also referred to as convection boundary condition, and the boundary value of y is unknown, i.e., where h, k, and T infinity are constant. So far, the types of BCs presented required y and or y' at a boundary. Another important type of boundary condition encountered in practice is called a periodic boundary condition. This boundary condition type does not require additional equations for the physical boundaries. A periodic boundary condition implies that the ordinary differential equation solution on a closed interval from a to b is periodic with a period, t equals b minus a. That is, the boundary conditions can be simply stated as follows. In the subsequent illustrations, we will denote the check mark or symbol for a node whose solution is known, i.e., case of Dirichlet boundary condition, and the circled X mark or symbol for a node whose solution is unknown, i.e., cases of Neumann or Robin boundary condition. That is all for now. See you next time with another topic. Bye.